うん。ああ、疲れた。お茶作るか。なんか他のお菓子が必要な気がするな。茶菓子っていうか。New one, welcome back. Sorry, drop this. Actually, I'm not listening to anything. Let's throw that to the side. Yeah. No, I had headphones. Um, and it just kind of fell off the desk. Oh man, so tired. I already did so much reading today. I kind of don't want to do any more reading, but I kind of need to. So yeah. Well, actually, so the thing is, I haven't actually had dinner yet. Had a little bit of a late snack, so I'm starting to get hungry, but I'm not entirely hungry yet. I think what I'll do is I'll read a little bit, and then I'll go get dinner, and then I'll work on something more fun. Yeah. I I'm a little bit uh troubled by how much money I've been spending recently, but um we're almost caught up with everything, so I figure I can start doing more like meal prep or stuff after that. We'll see. Uh, move this over here too before I drop it. No. Actually, the main thing I need right now is I need a nice like snack to go with tea. I I think I have everything else kind of prepped in this office. You know, I got kind of more savory or like salty snacks for, just like with to go with soda. I've got instant noodles for if I ever forget lunch. I got breakfast. I got like cereal and oatmeal, and I got milk in the fridge. I don't have any snacks to eat with with tea though, like sweet snacks. Should I some like I'm thinking like cover? This is oh oh I just realized I don't have a screen for showing the camera zoomed in. Here, I'll unblur it real quick. Here you go. Or oh, no. Why did I move? Let's see. There we go. Lock myself in place. Yeah. I think it's been a good read so far. Admittedly, I haven't gotten that far into it, but yeah. Well, I've gotten only like a handful of pages in, and there's already this many fucking notes. So you can kind of imagine the information density of it. It's a little bit of an easier read than some other books, but it's still dense. One of my colleagues was like, "Yeah, so how's the thing you're working on going?" And I was like, "Oh, I'm still reading." And they're like, "Oh, what part have you gotten?" And I was like, "The intro." Yeah. And part of the reason why is there's and this is something I do like, the author makes sure to has like little like asides and little like examples to kind of really kind of contextualize the information, which is good, but it kind of puts you on like a different rabbit hole every subsection, just trying to figure out, okay, what is this example actually trying to say? So yeah. So like there's a whole like literally the beginning of the book starts out with an example of or to kind of say contextualize uh I guess so the author starts with like the conceptual design of an experiment really. And one example he uses is two photon Doppler free spectroscopy, which is a very smart idea, right? Because if you use just say one photon or one high energy photon, and you hit a particle, then just due to the at relativistic speeds, right? Just due to the Doppler effect, the amount of energy imparted on the particle shifts by well, based on whether the particle is heading towards it or away from it, right? Like a particle heading towards the photon you shoot at it is going to see the particle coming at it Doppler shifted, and then vice versa. If it's heading away, it's going to see it Doppler shifted in the other direction. So this experiment fundamentally, the spectroscopy method is to say, well, you hit it with two photons from either direction, and that way one photon is Doppler shifted like negatively, and one is Doppler shifted to look like lower energy, and the other is Doppler shifted to look like higher energy. But since they both hit the particle at the same time, you end up putting exactly two photons worth of energy into the particle, precisely. So you're kind of using the fact that it's Doppler shifted, but you're kind of just then saying, okay, well, if I shift one higher and the other lower, then you'll end up putting two photons in. So cool. You just to make sure then those two photons is equal to the jump in energy levels for that particle that you're targeting, right? But I was like, okay, that makes sense. But then there's little asides, like I guess there's some kind of like beam chopping going on here, like the excitation, like the thing shooting the photons. I guess you have to like chop or something, and I don't quite understand what the relevance of that is. But there's like little asides that go into very tangible examples, which I like, right? Because it's very clear, like here is a very explicit case in where such and such idea is used, but admittedly and I do prefer it that way. It's just it does lead to it kind of means for every paragraph that I read I need to spend maybe like 30 minutes to an hour just kind of like thinking about it and like looking it up and stuff, right? So, you know, you got to pick your poison, right? And I think, again, I prefer it kind of this way because it kind of at least provides some context or some relevance to like, or it kind of, you know, outlines the relevance of what the heck I'm reading, you know? So I do kind of prefer it this way, but admittedly, that's why it takes so long to get through this, you know, even the intro, right? Like, how many pages is this intro? It's, I'm on page like 9, and it's like, goes up to like page like 50. That's not true. It goes up to like page 40. Goes to exactly page 40. So, see, exaggerations. Yeah. But I'll do a little bit more reading. I've just done so much already today that I think I'm just going to do a little bit more and then probably pivot to something else just so I don't get too tired. Actually, wait, did I did I choose the right tea? Caffeine free. Yes. Okay. I was like, I don't want to be stuck all night or stuck, you know, awake all night. All right, so let's get back to this. Actually, one thing I guess I got to work on is I got to make an OBS scene for having the camera in you know being the focus. I got to do that. Actually, it keeps trying to autofocus. Stop trying to autofocus. Can I at least change that? Sorry, there's nothing problematic on my screen, right? Yeah, so I can go back here real quick and are there any autofocus controls? Configure video. Here, disable. How does that work? So let's see. So is focus disabled now? Because then if I throw this up, does it autofocus to the thing I have up here? I don't think so, right? I should have to do this, yeah. And then I'd have to manually... There we go. Okay. And then I think... Yeah, I think the stuff down here is just so far away that everything is out of focus, but I can't really do much about that. But I think I'd rather have it focused that far back and then I'll blur it anyway. But this way it's not, at least it's not like, you know, flickering, trying to focus all the time, so. Or not flickering, but it's not trying to constantly auto-adjust, so it's a little better. Okay, so, alright, so I guess this is more verbal notes for myself again, but actually, you know, I guess I could change the title of the stream, right? I guess I probably should do that too. So let's see, edit settings, and then we'll just say reading, oh, text. Reading, building electro-optical systems. Put the author in the title. Hobbs with the S, yeah. I think electro-optical systems, yes, okay. I'm not going to put the full title because it's, I think... Actually, wait, here. I should do this. I should put a semicolon there, or not a semicolon, I should put a colon there. That way it's clear what the title of the book actually is. There we go. Fancy. Fancy. Anyway. Actually, is this blurred? Is this camera view actually blurred? That looks pretty much unblurred. Did I forget to apply a blur to this? No, it's definitely there. It's just when I get close enough, it's basically as if there is no blur. Did I apply the right... Oh, that's why. Okay, I think it's unblurred by a factor of 2. There we go. There we go. Now it should be hard to read, right? Oh, no, it's still pretty easy to, whatever. It's close enough. Okay. Back to work. Right, so where did we leave off? So, I guess what we said was, in practice, when calculating wave propagation, we make four main approximations. The first is assuming scalar optics, which says we replace vector field addition with scalar addition, as one simplification, obviously. The second is paraxial propagation, or i.e., we make, or instead of assuming, why do we make the paraxial approximation? Let's see. So the paraxial wave function or wave equation is taking, or let's see. So you derive the paraxial wave equation by taking a standard plane wave and then multiplying it, yeah. So you multiply an envelope function with a plane wave, and then you shove it in the Helmholtz equation, which is over here. What do you call it? Oh, it's the Helmholtz equation. It's energy related, or it's, some jazz like that, right? And the whole point of that is by multiplying the envelope function, as they call it, you're kind of taking, or you're kind of incorporating the, what is the, oh, let me read this section again. I read this early in the day and I didn't have my coffee then. Right, so let's see. Gaussian beams don't satisfy the true scalar Helmholtz equation because their phase fronts are paraboidal rather than spherical, and because they extend to infinity, both real and K space. Okay. Well, at the very least in my head, I was kind of treating it as, in practice, we deal with Gaussian beams, not perfect plane waves, right? And therefore, if we're, again, computing the propagation of waves from, like, say, a light source that we have, then it makes sense that we use a wave equation that takes into account the Gaussianness. And I guess a Gaussian wave is a particular solution to the paraxial wave equation, and hence we use that as approximation. So the approximation being the paraxial wave equation. Or at least that was my understanding for why we do that. Again, it's still a little bit iffy in my head. There's some, like, math terminology in here that I had to Google and shit, so I don't admittedly quite understand that, but yeah, like, there's a little stuff here, like, for example, they talk about so a propagator makes sense to me. So a propagator, they say, is an integral operator that uses the field values on a surface to predict those in the entire space. So it makes sense, right? You have a field at a point, and then you use the propagator to say, okay, if this propagates into space, then what does the entire field around, that it generates look like? Like, okay, so the propagator thing makes sense. So you have a kernel. Let's see. This author says the Huygens maybe kernel depends only on x minus x prime, or vector, and so is a convolution, leading naturally to a Fourier space interpretation. I don't really know what that means. In fact, I didn't really know what a kernel meant. So yeah. So I guess, I looked up the definition. So in mathematics, the kernel of a linear map is, i.e. null space is the linear subspace of the domain of the map, which is mapped to the zero vector. Did these people not learn in like elementary school to not use the word in the definition? Actually, no, I guess that's fair because they don't use kernel in the definition. They use map a bunch. So then I was like, okay, what is a linear map then? And then the definition is like a linear map is a mapping V to W between two vector spaces that preserves the operations of vector addition and scalar multiplication. I was like, oh, okay. Yes, that totally clears it up for me. I have to do some more. I mean, those phrases I recall from vector algebra, but or linear algebra, but admittedly, I didn't do super well in that class either. Okay. But anyway, yeah, so that's what I assume the paraxial propagation thing is. We're using the Huygens, I guess, integral as a propagator, as in we kind of take into account the paraxial or not what. Yeah, right. So we modify the Helmholtz equation so that it's applicable to, or we modify the Helmholtz equation. That's not true. Because we use the Helmholtz equation as it is, but we just plug in something that isn't technically a solution, and we do some approximations to yield a wave equation that to some extent approximates, what we see. Yeah. So beyond that, I'm not quite sure what they mean by paraxial approximation. Okay, so Gaussian beams. The Gauss-Legendre beams are particular solutions of well, it says right there. The general form of a zero-order Gauss-Legendre beam that travels along the z-axis in the positive direction and whose phase fronts are planar at z equals 0. Excuse me. Is one thing I said I was gonna do is every single time a Greek letter popped up, I was gonna write down how you fucking pronounce it. Let's see. Greek letters. So this one is phi. So phi a function of x, y, z, and t is equal to some big mess. And they say where r, and there is several z-dependent functions in here. Where I guess we have function r of z, which is the radius of curvature of the wave fronts. I guess let me put that as quick reference, actually. I don't want to accidentally tear the paper, or tear the book. Let's see, R of Z is the radius of curvature. Of phase fronts. Actually, that's good. Sorry, just to verify. A phase front is, I think, the line or plane or some surface of constant phase. I should double check that. And has a lowercase phi as a function of z. This is the envelope phase shift. Envelope phase shift. W of z. Which is the 1 over e squared power density radius. I really don't know what any of these things are. 1 over e squared power density radius. As z sub r, which is the Rayleigh range. It's amazing they have names for all these things. And W naught, which I imagine is, yeah, the beam waist radius. Yeah. It says these parameters depend only on the beam waist radius W naught and the wavelength lambda of the light in the medium. Is that true? Let's see. So R sub Z depends on Z and Z sub R. That sounds like a fucking lie then. But Z sub R definitely depends on pi W naught squared over lambda, so that's true. So Z sub R is definitely just dependent on W naught and lambda. But what about Z? Its R function of Z is Z plus Z sub R. I assume Z is the, this is the direction. Oh, I see. At Z equals 0. Well, no, that's infinite. So maybe they meant to say Z and, you know, W naught and lambda or something. Whatever. So they say the envelope function, which is phi, is so this entire thing we have right here is complex, which means that it modulates both amplitude and the phase phi, lowercase, of the associated plane wave. This gives rise to the curved wave fronts, surfaces of constant phase. Oh, right, yeah, so I said earlier, what was I looking for? What is a phase front? A phase front is a surface of constant phase, yeah. I think that might have come up a different time, but I don't really think about it until now. Let's see. So it sounds like a wavefront and a phase front are identical then. In fact, I guess Google says wave, or when you type in phase front, um, it links you to wavefront, or it recommends wavefront. So yeah. Anyway. So let me double check. Did I properly clock out of work today? I'm pretty sure I did. Yes. Yeah. Right. So the envelope function is complex, right? Which means it both modulate. Which means that it modulates both the amplitude and the phase phi of the associated plane wave. This gives rise to the curved wave fronts of focused beams, and also to less well-known variations in d phi dz with focal position. The GUI phase shift. A GUI? GUI? I don't know. GUI phase shift. Let me read the page on wave fronts real quick. Sorry, I just thought of something, which is why I kind of shut up. But hmm, sorry, just, I don't know. Something just randomly popped into my head. But I just went to. Let me see. Sorry, so my notes from today's little colloquium. Or actually, does that actually make sense? So I guess their system uses Hmm. Well, I guess when scanning we do that anyway, so it shouldn't be that much of a difference to... Yeah, okay. Alright, so anyway, that little idea I had can kind of go on the side now. And it's past 9 o'clock. So the question is, oh, okay, how about this? How long is this section? Let's get up to the bottom of 1.3.4. Yeah. Right. So, I don't quite see why the envelope function being complex means that. Let's see, wait, so let me say so. Try to work out the math real quick. So the envelope function is usually, or is multiplied to the carrier, right? So you have b times e to the I kz minus omega t. And they're saying when this function is complex, so it's like phi sub, I guess, real plus phi sub like I or something times e to the I kz minus omega t, which this breaks down into this breaks down into cosine plus I sine whatever, multiplied again by the two real and imaginary components here. Yeah, I don't necessarily see that. Okay. Whatever, but this gives rise to curved wave fronts. Okay. Yes, these are words. Okay. I mean, I can kind of see it's the same thing with how a complex or a complex magnitude for like the where is it? It's just like how you get like circular and versus elliptical polarization for a propagating plane wave, right? Like if the leading if the what do you call it, the amplitude component, so to speak, yes, here. E naught, let's see, simplest solution for a vector plane wave, E of x equals E naught e to the I, or sorry, E naught magnitude, that's not magnitude actually, it's E vector equals E naught vector times exponential E to the I k dot x. And then they say if E naught there is real and imaginary, then it's going to be circularly or elliptically polarized based on what the magnitude of each of those components are. And I imagine it's a similar case here, except instead of e to the ikx, you have the carrier plane wave, or the plane wave carrier, which is e to the ikz minus omega t, and the thing you're multiplying. So it's this. I think that it's somewhat, related. I don't quite go anyway. And this gives, so I don't know how that necessarily leads to a curved wavefront, but I can see how it leads to something that is curved. Let's see. Why does that? Okay, so surfaces of constant phase. So the idea is if you multiply this by, or the carrier by the what do you call it? The envelope, then what? Then the surfaces of constant phase Well, actually, yeah. So they're saying the envelope, or sorry, the envelope function. Is it envelope or envelope? I don't know. Um, but the function is complex, which means it modulates both amplitude and phase. If we take that just for granted without really thinking about how exactly that works, then it makes sense that the phase phi, which is again modulated due to the envelope function, uh, is, well, it's modulated, but how does that necessarily mean that it results in a curved wavefront? Yeah. So maybe that's a question for later. Yeah, I don't get it. Okay, and there's this other thing. The GUI phase shift. I don't get it. Ow. Anyway, Gaussian beams reproduce the ordinary properties that mean of small to moderate numerical aperture. They also form a complete set of basis functions, which means that any solution of 1.22 can be described as the sum of Gaussian beams. 1.22. 1.22 is the paraxial wave equation. Let's see. So at large Z, the Gaussian beam looks like a spherical wave with a Gaussian cutoff in U and V, but for small Z, it appears to be a collimated beam. Reasonable limit to this region is where the beam area is twice that of the beam waist. The axial distance from the waist to this point is called the Rayleigh range. Okay. Goes as 1 over numerical aperture squared. The beam waist goes as 1 over numerical aperture, and angular width as numerical aperture. At z equals plus minus Rayleigh range, 1 over e squared beam diameter is increased by a factor of square root 2 so that the central intensity is halved. Okay. Okay. So what is the takeaway here? The z is the propagation direction of the Gaussian beam that we're talking about. So at large propagation distances, the Gaussian beam looks like a spherical wave with some Gaussian cutoff. Not really sure what they mean by Gaussian cutoff, but if we assume it's like a Gaussian filter, then okay, it's a spherical wave with some kind of filter that makes it kind of look, you know, mainly in the middle and, you know, exponentially dies out. Or I mean not exponentially, but it's a Gaussian. Okay. Well, we'll assume that's the right interpretation. Okay. And then say, okay, so for small z, as in for small propagation distances of this beam, it appears to be a collimated beam. Collimated as in it doesn't diverge, right? Yeah, parallel rays, yeah. That... I mean, okay, so what does a Gaussian beam even look like? Like, in space. I mean, I guess is the idea that if you just get so close to the light source, then it all looks fucking parallel because it's all coming at you. I mean, I guess in that sense, yeah, I can see that. Oh, hey, what? Well, here we go. Edmund Optics has a good thing. Okay, so this image helps. Go. There we go. We'll put a little memo to see Edmund Optics, yeah. Okay. So Hobbes says here, the Gaussian beam is a paraxial animal. It's hard to make good ones of high NA. Let's see, NA is numerical aperture. What does it mean for a beam to have high NA? I know lenses can have high NA, and that's in some sense related to the, or I think it has something to do with the maximum angle it can accept light at. Something like that. Where's that? There's some notes about it somewhere in here. Thought I wrote something. It's a problem about taking notes, right? You think you wrote something down and you didn't. It's about isotropy. Sure. Here it is, numerical aperture. Yeah, Wikipedia uses a definition that says a dimensionless number that characterizes the range of angles over which the system can accept or emit light. So, that's kind of an optics definition, but in this case, they're using it to talk about the beam itself, right? So, a Gaussian beam with high NA. Does that mean... So the theta in the definition of NA is the half angle, or like the inner angle of the cone formed by some light source. But I guess if the beam is shaped Gaussian, then that means the edges of the beam, as you make like a cone of it, are a lot dimmer than the center. So maybe in that sense, they're saying you can't make a super high angle one because it's like it's just not super contained or something. Let's read this article a little bit. Well, let's just put this memo in and keep going. Alright, so I'm getting a little unfocused and, well, mainly I'm getting a little hungry. So, I'm gonna go get some food. What should I get today? Yeah. Yeah, well, the main thing is just I'm kind of losing focus. Um, yeah, it's the problem with these long greetings. Anyway, yeah, I'm gonna probably just cut the stream. No point in leaving it on. I might come back afterwards. That's gonna be pretty late, but yeah, we'll see. We'll see. I might just let me get food and then I'll think. But anyway, yeah. So, new one. Thanks for popping by. I'll catch you maybe later today, maybe some other time. Uh, but yeah, yeah, I don't know. I might start the stream again later, but yeah, I wouldn't count on it. Right. Anyway, yeah. See you later. Let's go to.